Juliette Becker from Caltech, and she's giving us an invited talk on the origins of multiplanet systems with misaligned nearby companions.
All right. First of all, thank you guys all so much for putting on such a wonderful conference. Even though we didn't all get to meet up in person at Riverside, it's been really nice to see all the people working on exoplanets in the Southern California community, especially the new postdocs and students. So today what I'm going to talk about is one particular architecture of exoplanet systems, which is tightly packed systems with many planets that have misalignments between some of those planets. And although it's only a single architecture, the things I'm going to talk about that could have caused this architecture are going to be more broadly applicable to other exoplanet systems as well. So kind of what I'm going to take you through today is the story of how do we go from a single system and its potentially unique architecture to broader mechanisms that can affect both that system and the population as a whole. So in terms of understanding exoplanet architectures, we're not quite at the very beginnings anymore, because now we have many types of architectures that have been discovered with Kepler tests and supplementary data from RV missions and otherwise. But we're getting to the point where we're starting to see what kinds of systems are more common and what kinds of systems are less common. And hopefully soon we'll be getting to the point where the systems that are apparently outliers will eventually become parts of larger populations. So first, let's talk a little bit about the Kepler sample as a whole, what it taught us, and some insights that we can make about those systems. So I'm going to start with something that you guys all probably know. So I'm showing this image from Lauren Weiss's Peas in a Pod paper, where she plotted all of the systems with 4 or more planets from the Kepler sample. And one system there that's not from the Kepler sample, that would be our own star, our own sun, and showed the relative spacings and semi-major axes as well as their relative radii. So if you look at this x-axis, you'll notice that that is ranging between a little bit more than 0.01 AU, and most of the planets fall within half an AU. And what this has taught us is it's taught us that these multi-planet systems are pretty common. So some of the numbers that you can put on that come from Muirhead et al. 2015, Zhao et al. 2018. About 20 to 30% of systems may host some tightly packed multi-planet system. Now, this is an architecture that we don't have in the solar system, because if you look at the Sol indication there, the solar system terrestrial planets are a little bit further out than the typical Kepler system. But what we did learn is that all of these systems, by definition of their discovery method, which is transit photometry, are fairly tightly packed in inclination space. So a 2014 empirical study by Dan Fabrici showed that in general, these planets are drawn from a Rayleigh distribution with a width of about 1.4 degrees. And this is partially an observational bias, but it's partially an architecture that all of these systems tend to be fairly tightly packed. Next up, Kepler taught us another thing about a different population of planets, ultra-short period planets. So ultra-short period planets are planets with orbital periods of less than a day or so. And these are relatively rare. So they occur in about 0.5% of systems. That comes from San Jose 2015. These short period planets sometimes have been found to have decaying orbits. Sometimes they've been found to be disintegrating and have asymmetric transits. So they actually encompass a wide variety of dynamical states, from on the edge of stability, such as those 2 cases I've just mentioned, to systems that are stable for a longer term. Okay, so we have 2 different types of planets, ultra short period planets, and then your more typical multi-planet system that contains a lot of planets, tightly packed, pretty quiet orbits. One final thing we should know from the literature is the inclination distribution of all of these types of planets. So this result comes from Day et al. 2018, and it shows the mutual inclination of pairs of planets plotted against the separation from the stellar radius. And what you should notice from this plot is when you look on the outskirts at larger major axis ratios, the mutual inclinations of the planets doesn't populate the entire regime in which planets would transit. So this black line here shows the upper envelope of mutual inclinations that would be detectable via transit photometry. So if you had a system with a mutual inclination above this line, you wouldn't expect to have seen it in the Kepler data anyway. But you'll notice that there is a actual lot of space in between the upper envelope of the data here and the line that defines allowable planets. So what that means is that for at least the systems with larger semi-major axis over stellar ratios, so the ones where the planets are further out, we probably are detecting the system pretty reliably. We don't expect that the envelope extends much beyond what we're looking at so far. In contrast, if you look at the systems with shorter orbital periods closer to their stars, which includes in this regime the ultra-short period planets, what you'll see in that regime is that the mutual inclinations populate a much larger fraction of the possible parameter space that could have planets be discovered. So what this means is that potentially there's more inclination dispersion in short period, ultra-short period planets and shorter period planets than there are in longer period planets in these multi-planet systems. So it's kind of a dichotomy that's occurring inside exoplanet systems. So you could have a single system that contained an ultra-short period planet and then also a collection of outer planets and maybe have different mutual inclinations within the population. The reason this is interesting is because if you make assumptions that these planets probably formed from some kind of disk-driven migration mechanism, which is an idea that's kind of supported by the idea that we see a lot of these planet pairs being in or close to resonance, and resonance is thought to be easily formed if you migrate in a disk, much more difficult to form if you did not migrate in a disk. What this suggests is that even a disk-driven migration mechanism that forms these high multiplicity systems will still sometimes have these misaligned inner planets. So it's kind of a interesting idea, but again, from this diagram, you can't necessarily tell what planets correlate in the same system. So to study this effect, to figure out how can we reconcile this idea of ultra-short period planets having higher mutual inclinations with their systems, while longer period multi-planet systems tend to be fairly well confined in inclination, we can look at a case study that shows both of these effects in the same system. So the case study that we're looking at for this work that represents both of these geometries is K2266. So what I'm showing you here is the transit light curves. This is from K2 data, as the name implies, for all of the planets and planet candidates in the system. There's a few interesting things to point out. So the first thing to point out is that these two planets, which are both confirmed, and they were confirmed via transit timing variations. They had anti-correlated TTVs that we saw in the Kepler data, so we were able to confirm their planetary nature and find mass constraints. But these two planets are pretty close to resonance, the 4 to 3. So what this suggests is that this K2266 system should have assembled via a mechanism that allowed these two planets to end up close to resonance. I'm not going to say in resonance because we don't really know if they're in resonance, but they're at least close to resonance. Additionally, another interesting thing in the system is you can probably tell from the orbital period of the left panel, we had one ultra-short period planet in this system that had a period of 0.6 days. And this is actually a grazing transit. So the inclination that we measure from the fact that this transit was barely visible, we didn't see the whole planet pass in front of the star, we only saw part of it. This infers a mutual inclination of between 14 and 17 degrees to the other planets in the system. So the outer planets are all fairly tightly confined to a plane within less than a degree of each other. And then the innermost ultra-short period planet is tilted relative to the rest of the planets. So this pretty well encapsulates those two populations I was talking about, the ultra-short period planets, which can assume a wider variety of inclination values, and the more typical STIPs, which have lower mutual inclinations, sometimes have resonance, have a lot of planets. I should also point out that in this particular system, 2 of these planets we did not validate in the paper, one at 6 days and one at 56 days. And both of these 2 planets would, if real, have radii of about half an Earth radii. So we did not validate these planets because they were just too small. The signal to noise of the transit events was too low to validate as a true planet. So hopefully, maybe in the future, someday, more data might increase that signal to noise. But for now, we have at least 4 validated confirmed planets in the system that we trust. And before I move on, the rest of this presentation, I'm going to be talking about only K2266. But there are more systems with this geometry. So although most of these tightly packed high multiplicity systems that contain ultra-short period planets do not have such extreme misalignments between the inner and outer components, one other system that does match this geometry is TOI 125, which is a test system, as its name implies. So this next slide shows a schematic of kind of what the system looks like. So what I've tried to show in this art that I've drawn is that the ultra-short period planet closest to the star at about 0.6 days in the system is tilted relative to the entire system of outer planets, the STIP. So the STIP is pretty well confined. You can kind of think of that as just a disk of mass. Like all the planets together are fairly highly coupled to each other. They kind of move together as a disk most of the time. We'll talk more about that later. But the ultra-short period planet resides in a very different state. It has a very different angular momentum direction than the other planets. So if we want to create a system that looks like this, there are two components that we have to, there are the two conditions that we have to meet. First, you have to somehow create the misalignment between the ultra-short period planet and these STIPs. So if we're operating under the assumption that these planets all formed in a protoplanetary disk, there would be no native misalignment between them. So some other process would have to cause that after the planets formed. And the process could occur at any time. It could occur while the disk is still present. It could occur after the disk is dissipated, before the planets have migrated, after the planets have migrated. But in any case, we do need to allow this misalignment to both be created and also maintained so that it's observable today. Secondly, we need to keep the mutual inclination of the STIP low. So for K2266, we have a pretty strong constraint in the inclinations of the outer planets, both from the fact that they transit, but also from the shapes of the transit light curves. We know the planets are pretty close to the midplane of the star, not separated by more than a degree between all of the planets. And that's even accounting for the above, the below the plane degeneracy in the transit dips. So if we can meet both of these conditions, then we can create a system that looks like K2266. So our first goal is to figure out what are some options dynamically that create these two conditions and could have caused this system. After we evaluate those possibilities, we can determine which one's more likely. So there's two possible options that I'll talk about today. One is dynamics due to the exterior companion in the system, so an unknown planet. And then the other one is dynamics due to the stellar obliquity and the stellar quadrupole moment. So you don't have to invoke any extra planets, just if the star itself has an obliquity with respect to the system, as it decays, the dynamics could cause this architecture to form. So first, we're going to really briefly talk about the dynamics due to an exterior companion, which I'll explain at the end, I think is the less likely of these two explanations. So it's very plausible that this system has an additional planet that we don't know about in it. So here I show another schematic of the inner system and then an outer unseen companion that could really exist at any inclination. There is a huge parameter space in all of these transit systems where planets could reside and not be seen. As you increase the semi-major axis of the companion, the transit probability decreases. You know, at some point, even if you were aligned within 0.3 degrees of the STIP, you might not see the system anymore. So what we did is we ran a large number of numerical simulations in a Monte Carlo sampling scheme to just try and test if we injected an unseen companion into this system with a variety of orbital elements. So in this case, I'm showing the semi-major axis and inclination of that injected companion. Could we recreate the system geometry if we started from a coplanar inner system? So assuming that the ultra-short period planet and the STIP started out in the same orbital plane, the plane that they formed from the protoplanetary disk, then could you create the geometry we see today? And what I show here is the results of each of those simulations. So each simulation has been categorized by point style and color to describe what happened in that simulation. So this particular plot is for a companion mass of about Saturn, which is maybe a little on the large side for what we'd expect to occur around a 0.6, 0.7 solar mass star like K2266, but it's not completely impossible. For a Saturn mass companion, you'll notice there is a large regime of red points at a range of inclinations, but at shorter semi-major axes that are excluded because they cause the system to go dynamically unstable. So all all of those companions can be excluded because if they existed in the system, then we wouldn't see the inner system. The planets would have collided or something else would have happened that would have destabilized it. In contrast, at larger some major axes, you can see in brown, the companions that are too distant do not cause the ultra-short period planet to decouple from the STIP, and all of the planets remain in the same plane. So that also doesn't work. In blue, however, are the companions that create just the right dynamical phase space for the ultra-short period planet, that it remains more strongly coupled to the star than to the outer planet, while the STIP couples more strongly to the star. So the result of that is that you can get a mutual misalignment between the ultra-short period planet and the STIP, but the STIP will still precess the disk. So you won't excite mutual inclination between the planets that are a part of the STIP. So this blue regime could work. If a companion existed in any of those orbits, then that could potentially cause the observed geometry. So of course, a Saturn mass companion maybe is not reasonable. You can also look at the phase space areas that work for other companion masses. And what you'll notice is that you can actually put companions at places that in theory are physically realistic in the system. Remember, we're using transit inclination coordinates, so the current planets have an inclination of 90 degrees. Now, the difficulty here, of course, is if these companions exist, then in this particular system, we would require them to exist in very particular parts of parameter space. But it's also just as likely that these planets would not reside in this parameter space. So if you looked at a large ensemble of systems with this geometry, an ultra-short period planet and then a system of tightly packed planets, you'd expect a lot of those to exhibit one of those bad incomes on this previous plot: dynamical instability, a STIP that becomes too excited. And the one problem with this mechanism, with explaining the system of planets, is that we might expect to see a higher fraction of misalignments between ultra-short period planets and outer STIPs than we see currently if extra unseen planets were the answer. So if there were a lot of these, if there were these types of planets and systems, we might expect to see a different distribution of STIPs than we do today. So, you know, we can confirm if this is the answer, if we could get high fidelity observations that could rule out these parameter spaces, but this is not my preferred explanation for this effect currently. Now, the final and second mechanism that could also explain this particular geometry is dynamics due to stellar obliquity and the stellar quadrupole moment. So first, what do those two things mean? Stellar obliquity is just the tilt of the stellar spin axis with respect to the planetary orbits. So in the solar system, we have about a 6-degree tilt between the sun and the mean plane of the planets. It's not actually unheard of that systems could have stellar obliquities. We expect that it happens, although we do not yet have empirical estimations for how common or what magnitude of obliquity should exist. We know it's a possibility. So obliquity is the tilt. Secondly, the stellar quadrupole moment is the oblateness of the star. So when stars are young and spin faster, they will have a higher quadrupole moment, which means that they're more deformed, and their gravitational field will have a non-spherical term, which is stronger the more deformed the star is. Together, these two effects alter the planet orbits. So what I'm showing here is also, this is from numerical simulations. We have two metrics that describe the architecture of our systems as they depend on the stellar J2. Now, J2, the quadrupole moment, remember, it decreases as stars age. So a young, rapidly rotating star might have a J2 of around 10 to the 2, 10 to the 3, 10 to the 4, while an older star will have something around 10 to the 8. So this is, again, a kind of grid search of stellar J2 values where we simulated the K2266 system as if it had started out in the disk, and it was subject to the quadrupole moment of each of these grid points. And what we find is the two metrics. So in orange, we have the misalignment between the ultra-short period planets and the STIP. And at high values, the resonance is outside of the STIP. So we don't actually get any decoupling with the due to the stellar quadrupole moment between the ultra-short period planet and the STIP. However, when you reach a stellar J2 of around 10 to the -6, what you see is a misalignment starts to arise. And then lower values than that, the resonance is interior to the ultra-short period planet. So if you have a J2 of like 10 to the negative 8, 10 to the negative 9, nothing will happen. In green, we have the mutual inclination of the outer system, because remember, as the secular resonance sweeps through the system, it can also cause the SIP planets to become misaligned relative to each other. And what this tells us is if the J2 is too high, if the star is too young, then if the SIP planets reach their final orbital positions while still spinning rapidly, they will become dispersed in inclination relative to each other as well. So what does this mean? We can't read off this plot the value of J2 that the planets arrived at their final orbital positions at, because as J2 evolves, the phase space area of the system will change. This is a diagram that shows approximately what we expect the J2 moment to have done for the K2266 system. Now, measuring the quadrupole moment is not something that we can do in the past. We have to make extrapolations based on stellar models, which we can't do very well for M dwarfs, but for larger stars like K2266, we can make approximations. So I'll get back to this diagram. Basically, the idea is as the star ages, the J2 moment is going to decrease. Now, what we would really like to do is model the evolution from the birth of the system to present day. This is not something we can do with numerical simulations because the time step was so small that I would be sitting here running simulations all year. So instead, what we use is we use the secular model. So the first thing that you can do is you can write a Hamiltonian, a really basic Hamiltonian that includes planet-planet interactions between the ultra-short period planet and the SIP, as well as GR and the precession due to the deformation of the star. From this simple Hamiltonian, you can solve Hamilton's equations and find the equation of motion for the inclination and the longitude of the ascending node. So these are the coordinates that are related to each other. So if you find these equations of motion, then that tells you as time increases or as J2 decreases, how is the inclination of the ultra short period planet going to change with time? So here's an animation showing exactly what happens. It's going to loop through a few times. What you'll notice is that as J2 is big, so around 10 to the negative 2, 10 to the negative 3, the ultra short period planet is coupled very strongly to the star and the inclination is low. As the star ages and the J2 term in the Hamiltonian becomes less important, then the ultra short period planet starts to decouple from the quadrupole moment, and the frequencies due to planet-planet interactions become more important. And that allows the ultra short period planet to become, to increase its inclination with time. So we can take this animation and we can turn it into a plot so we can actually see what's happening. So on this plot, I have plotted the orbital inclination of the ultra short period planet as compared to the stellar J2. So if we were looking at the evolution of a single planet, you'd start in the outer system where the J2 is high. So see the red point there. And then as time goes on, you would move to lower J2. And as the stellar quadrupole moment decays, you would decouple with that and couple with the planetary system. Now, what this means is that if this mechanism is why we see these misalignments, we actually would expect as time goes on, these ultra short period planets would eventually couple with the SIP and you would no longer see these misalignments. So if we could get to a system that had a J2 of 10 to the negative 9 or larger in the K2266 system, which would be a very old system, then in theory, you would see this misalignment stop existing. So basically what we're doing is we are taking a snapshot as the evolution is happening at the current value of J2, like right here, whatever it is. And then that's the state of the system that we are currently observing. Now, one major caveat on this is, again, we don't actually know the current J2 value for this star. So for K2266, we don't actually know the rotation rate, the current day rotation rate. So this plot inset with the shaded blue region shows the possible range of J2 values at each stellar age, which you'll notice there's a pretty wide range of values possible at any stellar age. So if we want to do better than just providing a potential mechanism that works, the next thing that we need to do is do a better job at constraining both our models for how the quadrupole moment changes as the star ages, as well as, of course, do a better job understanding the rotation rate of the star, the quadrupole moment of the star, the true obliquity of the star if possible. So those types of measurements will be incredibly useful to refining our dynamical models moving forward. So There are two mechanisms that I presented today that work to create a geometry like K2266. I've ordered them here in order of my preference of how likely I think they are. The exterior companion has some issues because if there's an exterior companion causing this dynamics, there's no reason that this system is the only system to have such a companion. Like they should exist across the population of SIPs. Secondarily, if the companion needs to be inclined, something else in the system would have had to cause that in the past. And it's possible something like a broken disc could do that, but that seems less likely than the very natural stellar obliquity and quadrupole moment evolution, which we know that every star will go through the stellar quadrupole evolution, and a decent fraction of them should have some non-negligible stellar obliquity. So this was a case study of K2266, which kind of shows how you can take a single outlier system from the transit data and learn a lot about what mechanisms are possible in systems like this. So thank you all so much for paying attention today, and I'd love to take any questions right now.
Thank you. Thanks, Juliette. That was a great talk. Let me flip over and see if we already have questions in here. I don't see a question yet, so I'll ask. I just had a question regarding observations. Do you have an idea of what observations you specifically need, or like how large of a sample to determine which of these mechanisms is primarily at work?
Yeah, so I would love stellar obliquities. Now, stellar obliquities are easier to do for larger planets. So most of the stellar obliquities that have been done are with respect to hot Jupiters because it's a lot easier detection. But if we could get stellar obliquities from multi-planet systems, that would be extremely helpful. Kind of lower hanging fruit is rotation rates. So that's like, ideally I would like the rotation rate, the V sin I, all of that. And that would be extremely helpful for constraining the star direction.
Okay, thank you. I see we have questions pouring in now. From Marshall Johnson, they would like to know, sorry if I missed this, but in your model, is the USP already in its very short period orbit when the star is young and rapidly rotating? Does your model deal at all with how the USP got to where it is today? And nice talk.
Yeah, so that's a great question. So the original goal of this project was actually to find a way to constrain the time that the ultrashort period planet arrived at its final orbit, with the thought being that if you have a destabilizing process that would cause the SIP to scatter in inclination, then the system must have arrived in situ after that point. Unfortunately for this system, we were not able to make that constraint. So I didn't deal with the migrating ultrashort period planet, mainly because then we have the issue of the planet is moving through the system, but the location of the circular resonance is also moving through the system, which basically expands our parameter space by an annoying factor. But it would be an analysis that I would love to do in the future.
Great, thank you. Oh, I'm sorry, Will Meisner, I missed your question. Thanks for pointing that out. Will would like to know, is there hope of taking the measurements you need to better constrain your evolution models, and what techniques need to be improved?
So I think yes, I hope yes. So the obliquities themselves are taken via Doppler tomography or Rossiter-McLaughlin, which both depend on the RV signal while the planet is transiting. That's to get the stellar obliquity with respect to a planet. So as the precision capabilities of that method improves, then the masses of planets that it'll be possible to find those obliquities with respect to will also improve. So I think it's definitely possible, especially as telescope apertures get larger. The question is, will anyone give telescope time to do that kind of analysis on one system like this on a 30-meter class telescope? And I'm not sure about that one. So I think it'll be possible. It'll just be a hard science case to make. You'll have to be very convincing, or I'll have to be very convincing.
Okay, I think we have time for at least one more question from David Ciardi. I apologize if I mispronounced your name. Hi, Juliette. That was a really nice talk. Thank you. If the stellar obliquity quad moment is the explanation, one might expect stellar mass dependencies across the spectral types to be evident. maybe, can you comment?
Oh, yes. Okay, so that's a wonderful point. And I've kind of hit a roadblock with that one because you're completely right. To compute that, part of what you have to do is you have to know the history for the evolution of J2, which for larger star masses, I can kind of do. So that's fine. But for smaller star masses for M dwarfs, I do not understand how the rotation rates change with time. So the empirical measurements of current day estimated J2s for M dwarfs don't match what you get if you use a stellar wind model plus the Skumanich relation to model the J2. It's like several orders of magnitude lower empirically than what the theory would predict. So the potential answer is that there's an exponential fall off in rotation rates for M dwarfs. Okay, that probably happens, but I'm not sure when that happens. So that's if anyone knows the answer to that question of how the spin down of M dwarfs happens, like specifically, that would be super useful to know. That's the like one main thing that's blocking me from doing that next step.
Great. Well, thank you again, Juliette. I'll just kind of, so I'm not going to find that in time.